Alright, I should put 45 minutes in the schedule for debugging YouTube. So NDH loader just reads a header, and oh no, that's the offset. Oh, that's where the text starts in the file. Yeah, okay. So basically this loads in a file, takes an IO reader, which is just a file we've already opened, unpacks a header, which is some helper function I wrote, and returns a loader. And the only method we actually needed to implement on loader was segments, which returns one segment that says the file offset, the address we're loading at, the size of the text, and protections, and the actual data that's in the segment, which is just n.text, which we read up here with text. So I'm actually going to be working on a branch called NDH on my GitHub, and I'll just push this stuff as it gets done. So here I will go to here. I added these files. I'm just going to commit these and push them. So if you care too much what the exact diff is, you can look at that branch, and someone can probably link that in the stream if it's super interesting. Okay, the actual stuff here. We have arch. We need to make an NDH arch, and I'm going to add into arch.go preemptively. We need to import NDH, and we just need to say the name NDH goes to ndh.arch. So this is how architectures are looked up when a binary is loaded. Usercorn just calls this getArch function, which looks them up in this big map. So if we go into the NDH folder, now we're going to need an arch.go and ndh.go. Usually there would be different operating systems here, but NDH itself is kind of like a pseudo kernel that pretends it's something special, but really it's just a subset of Linux syscalls. So the setup here will be a couple of registers specific to the CPU, and then just syscalls into Linux. So in arch.go, I'm actually going to go copy the ARM one and mess it up. So here, instead of ARM, we have NDH. NDH, we don't need any of Capstone, Keystone, and Unicorn because those are our assembler, disassembler, and CPU emulator, and we don't have any of those. So we're actually going to define all of these as nil. We don't have any of this information yet. Let's assume that at the go/CPU/NDH path, I'm going to start implementing the CPU and disassembler. So I'm going to define ndh.pc, ndh.sp for the program counter and stack pointer, and then all of the registers, which registers 0 through 7, stack pointer, base pointer, and program counter. So, sorry if this is jarring, I'm switching to Sublime Text because I want to do text manipulation. So, I need, let's see, actually I've already got the register numbers in there. So 0 through 7. My keyboard is physically different. Okay. So instead of ARM, we've got NDH, reg, our 0 through our 7. And then we've got a program counter, base pointer, and stack pointer. This is totally the most exciting part of this. I'm joking. Is typing data into files. I was hoping to avoid this a little bit. I could potentially go partially into this and then hand wave pasting in the right enums too. Default regs is just going to be all of them. So this is the stuff that gets printed in the UI when you're debugging. So you don't have to print all the segments or whatever on x86. But here we don't care. We can just do everything but PC. Yeah. So here we don't need the enter user mode helper because this isn't ARM anymore. We don't need to enable FPU. So we have kind of an Arch definition here. Oh, the bits are wrong, and Radari doesn't support NDH, so I'm going to delete that. So this should be a working architecture definition, except for the fact that CPU and disassembler don't exist. So if I go and actually try to build this, oh, I didn't. Apparently, if you just touch an empty file and go, it will break the whole build. I did not know that. So I'm going to untouch my NDH file. Actually, I'm just going to say package NDH. And this is the wrong package because I copied it out of ARM. And this doesn't exist yet. So we've got some handy negative reinforcement development. It's the successor to test-driven development, where you write code that needs something and then you implement the thing it needs. So we've got an NDH CPU here, and I'm just going to make an enums.go. And this is package NDH again. If you're familiar with Go, you know I've now made 2 packages with the same name, and I'm a horrible person for doing that, but the import order means it will never matter. So, just close that. Package NDH, enums. I need all of the opcodes and syscalls and everything out of here. This is another super exciting thing where I look up data and show you how cool I am at text editors, but instead of doing that, I'm just going to copy it out of my notes as well, which basically I went and looked in all of the source of this and made sure the docs matched, and they didn't, and Graz helped with that a little bit too. So in CPU NDH, I'm going to grab my enums.go. I think it's enums.go. Let's see. This is going to be half a stream of me fighting with my computer, apparently. I really didn't want that. So all right, I found it. So this is all of the opcodes of the CPU, which to pull out of a header or something. The way the parsing works on these is described wonderfully in this fixed width thing. So this is a CPU with, the site doesn't even read that well, pretty few instructions. This isn't going to take, hopefully, as long as it has to fight with YouTube to actually implement the CPU. The CPU instructions are encoded as a single byte. Here it says here, it's a single byte that's the opcode, so that's add, and, call, comp, etc. A single byte if the instruction requires it, that's the flags, and then the operand 1 and 2, which are optional based on the flag that's provided. So some of these opcodes are only 1 byte and they don't take a flag. All the flag is it says what kind of register or immediate arguments the instruction takes. So here, if an op has the second byte of 0, it takes a register and a register. And then the addressing mode here was a shortcut I came up with in the data, so I didn't have to hard code a bunch of stuff that said whether or not an instruction took a flag. I actually had to go manually pull this out of the source code of the existing implementation because this isn't documented very well. So we have an incorrectly named enums.go. I actually named this ops.go. And I'm gonna call it, I don't know, defs.go. So I'm gonna put the CPU registers in here. So R1, oh, tab completion, fantastic. So that enabled now. So we have PC, BP, and SP. Okay, this is in the quest to make compile. Go. You have to say iota in Go. This is Go's magical enums, and we're going to add 3 flags registers too. That are separate registers. So the 0 flag, the after flag, and before flag. I think they just refer to them as letters, and some of the documentation is in French, which I do not speak, so let's see now. We don't use unicorn in the arch, and we don't use CPU in the arch. I'm gonna make this font size bigger too. So ndh.r0, oh, I forgot a reg. Okay, so we build, and I have an NDH samples folder with a couple of binaries that were from the CTF. I'm just going to copy to that to NDH hello. Fantastic. So we have a loader and it's loading, and the architecture doesn't have an operating system called NDH. So we have to go in here, take this empty NDH package, and I'm actually going to split these so they're a little easier to read. So if we look at any of the other ones, the x86 16 DOS implementation, it's actually long because it includes the entire kernel. CGC includes the entire kernel. What's one that I haven't really implemented yet? MIPS Linux is nice and short. Okay, so this is just a definition of a base kernel object, which in most cases will embed a more generic kernel. This is because, so this is the operating system definition for backend and usercorn. Most operating systems are kind of generic, or most architecture implementations of operating systems are pretty generic. So like the x86 Linux is mostly just Linux, which is mostly just POSIX, and there are like layers of syscalls on top of them. So the kernel infrastructure in usercorn is kind of tiered, so you can pull your syscalls in from multiple places. So there's an entire POSIX subsystem and a Linux subsystem, and Linux actually inherits from POSIX to get a bunch of the syscalls. So in the case of MIPS Linux, we just depend on the Linux kernel, which depends on the POSIX kernel. Here is a definition of the syscall ABI registers, which gets used to decode syscalls. Basically, the architecture-specific backend for an OS is a kernel, which can include custom syscalls that are architecture-specific, a function that returns the kernels, an initializer function that just sets up the stack, and in the case of Linux-based OSs, is usually just this, like Linux.stackinit. And then we have a syscall handling function that handles the syscall number lookups and the calling convention, which includes getting the syscall number out of the first register in most architectures, and then turning these Linux regs into a function. It's like a closure that returns, like actually gets the registers from the CPU, but there's a helper for that. And then the interrupt handler on MIPS. The interrupt handler on MIPS actually has to parse out some cause from the interrupt to dispatch a syscall, and at the bottom is the init function that registers this on top of the arch that's here. So this arch is a variable that we call register OS on with all of these functions. So we can copy this entire MIPS package over, it's no longer a bathroom break, not package MIPS, and delete a bunch of these that we don't need. I'm going to call this NDH regs. I really like code reuse. I believe the register arguments are R1. It's going to be NDH dot R2. NDH dot R3. Actually, we're already in NDH. I don't need that. No, that's from the CPU. Never mind. NDH.R4. I don't think they use anymore, but whatever. So when a syscall is called, it will use this array to grab the registers out of the CPU. It just calls the register read function on each of these values and returns them as a list of uint64s. So here we're going to have an NDH kernel and replace the MIPS kernel with it. And we're actually going to base the NDH kernel on the Linux kernel because it turns out they were lazy too, and it's basically just a bunch of wrappers around Linux syscalls. We don't need this. This is a thread local storage thing. This is already what we want. None of these are going to be named Linux anymore. Let's see, func Linux. And we're going to add the architecture called NDH. On NDH interrupt, we're going to actually use this for syscalls. How are these dispatched? Linux syscall U. So we're just going to call when an interrupt happens, NDH syscall. And the reason I'm just doing this is the hooking infrastructure can easily hook an interrupt from the CPU. So when you hit the syscall instruction, I'm just going to issue a hook for interrupt, and it'll actually plumb through all of usercorn and end up in this function automatically. And then NDH syscall, I believe the calling convention is R0 for the return value and syscall number. We're going to need a syscall table, so that's going to be sysnums, I don't know. And then we issue a syscall and write the return value. I'm ignoring a bunch of errors here because to do handle errors, because at this point, if you've gotten to making a syscall in your program, hopefully all of the invalid registers have already flushed themselves out. I should probably deal with that at some point, but it's never really been a problem. It's mainly a side effect of me getting apathetic sometimes about the way Go handles errors when it really doesn't matter in some cases. So we need a sysnums that we can actually, sysnums is a map of int to string. So for example, this, and these numbers, the syscall numbers get looked up and called as methods on the kernel, which is why we can reuse the Linux kernel, because if you go into something like IO, there's a getDents function. So if you called the syscall getDents, as long as the NDH backend maps your syscall number to this string, it'll do go reflection and find this function if it's in your kernel chain and call it. So because we've pulled in the Linux kernel, we can just define strings of syscall numbers. And I actually do have a table of those somewhere that I will go find as well. Because I don't think they were well formed in the docs at all. So yeah, this should make most of the syscalls work. I'm dubious about some of the socket ones, but If I remember correctly, they automatically bind to localhost. It's a CTF challenge, probably because in their 16-bit architecture, they didn't want to handle parsing struct sock adders, which are like a complex struct. Okay, so we have a basic kernel, and we're going to go back to our failure-based programming. DH.go line 13. I need an equals sign. Apparently I was printing something. And there's no NDH here. So I just need to import CPU NDH. Cool, it works. And now what we're getting is a seg fault when it's trying to, or a null pointer dereference. Yeah, invalid memory address or null pointer dereference. So it's getting a seg fault when it tries to start the CPU or when it tries to disassemble something, I'm not sure. So one of these two things is broken because it doesn't exist. So if we look in the Unicorn version, there's this type called builder that has a new function on it that just builder that has a function on it that hands you a new CPU. This is mostly useful because Unicorn has a bunch of different architecture and enum modes in it that you have to specify, so you can declare it like in MIPS. You say CPU.builder, arch.mips, then the mode and everything, or unicorn.builder. Instead of that, we're just going to have an empty object where the new CPU method returns an NDH CPU always. So we just want ndh.builder here. And then dis, we're just going to do ndh.dis as well. This is just an object that has a dis function on it. It takes in an address. No, it takes in a byte array of the data and a uint64 address and returns a list of instructions or an error. So we're going to be optimistically pre-declare these. We don't actually need an assembler because most of usercorn doesn't actually need an assembler to work. That's just for the fun toys, like assembly REPLs and stuff. So let's hide some of this. In Unicorn, let's add the NDH CPU and disassembler files. I do realize that at this point I've mostly just been bootstrapping code, but I will definitely think about how to make this process easier for people. So here we're just going to return a new NDH CPU and don't even care. And you can't have an error because we're just allocating. If allocation fails, it'll panic. And that should, nope, it doesn't. All right. And then we're going to type NDH CPU struct. And this is where all of the work I've already done starts coming in. I hate these import paths, but I haven't found a good solution for it yet. If somebody does have a good solution for this, I would love it. Probably godeps or something handles that. So go models CPU. This is the only part of it that has any meaning. So we can say CPU.hooks, keyboard shortcut, CPU.hooks, CPU.regs, and CPU.mem. And we will automatically get these subsystems. Oh, we actually need to initialize them here. So CPU is this. Fighting my keyboard now. And we say CPU.new hooks, CPU.new regs, CPU.new mem, and we need a doesn't end up doing that. All right. And then for each of these functions are going to need an initializer. I think regs is just a list of ints that's like R0, R1, R2, R3. And then BP, SP, PC, and ZF, AF, BF. So the 3 flags. Mem is just, I can go find the actual definition for that. So, in CPU, in models, CPU, models is a code name for fixes Go recursive imports by putting everything in the same folder. At some point I will re-architect that. The models folder basically has a bunch of types and then a bunch of helper functions. So models CPU has everything we need for custom CPU support. So mem, here we have the new mem function. I'm actually gonna split this. So we can have ndh.go, and then we can have mem, hooks, and regs, so we can get these initialized. So regs, oh, we need the bits as well. So it's a 16-bit architecture. And then in mem, we also need the bits. You don't really need the bits, it's just to throw errors if something goes horribly. Like if you start writing outside the memory range, it will throw an error automatically. And we need the byte order because it implements some helpers for reading numbers out of memory for you. Coding binary. And then for hooks, there's actually some circular referencing here. New hooks. I should really put it at the top of the file. Takes both CPU and mem in. So I have to say CPU.hooks equals. Oh, I ever used the name CPU. I can't do that because I'm also importing it. So let's see here. C.hooks equals CPU.new hooks with C and the memory object. And the reason you have to pass the memory into hooks is memory read write, memory fault, and everything are automatically dispatched with hooks. The hook subsystem is one of the big draws of usercorn and unicorn. It allows you to say something like this. So like on mem write, call this function with the address, the size, value, etc. And then do some code. And this code can even be to stop the CPU or to jump to a different spot or something. So a lot of the debugging functionality on usercorn is built on top of this. So we have probably a CPU. It's not going to conform to this CPU interface I talked about earlier yet because we need the start, stop, close, and handle functions, I think. So in here, models CPU, which of course it opens in the wrong group. All of the memory, register, and hook stuff comes from these 3 structure embeds. Structure embeds in Go are kind of like subclassing, but with simpler semantics. So hooks can't access anything on NDH CPU. It's just it's an attribute. Like if I called it hooks, the only difference is when you access an attribute or a method of NDH CPU, the method resolution order can include hooks if you leave it anonymous. It's just one way of handling that sort of thing. So we're missing the backend method. We're also missing start, stop, close, and backend. So we need these func NDH CPU. Nope, that's the wrong one. So here, and I'm going to return nil for all of these, and in is the backend. c.newregs. Oh, I was overzealous with my replacements. And I thought I fixed this. I guess I didn't. One of my default interfaces has the wrong type. So in the mem implementation, memReadInto is flipped. So I need to find the memReadInto function and just change the input arguments. Oh, I have to flip them here too. It calls itself. And I didn't name any of these, so they ended up in the wrong positions. I have a typo, and this thing should compile, and I'll push it. Yeah, ndh.dis, not nds.dis. And I didn't actually define that. So we're not going to implement that yet. Func d, I'm just going to look this up. These are the two disassemblers, and this is the assembler. So I can just copy this method signature and return nothing for now. We'll have a disassembler that doesn't do anything. I'll return nil nil. Go arrays are kind of cool. A nil slice or array is just a 0 length one, and if you try to append to it, because you can't, they're not, the lengths of them aren't mutable. If you return, or you can use nil basically anywhere you use one, and the append function will allocate one for you when it needs one. And then I need to import models here. Cool, so now we have an emulator that doesn't do anything. And we actually, oh, we're calling Linux.stack in it, and the Linux stack just gets allocated at a super high address, so I'll need to fix that too. Instead of calling Linux.stack in it, we're going to do u.map stack ox0x 8000, so it's the first 8000. And let's switch syntax here. So, oh, that's whether to implement a guard page. I don't want that because we'd run out of memory. So we can't map an extra page at the end of our 16-bit address space. Now I think it's just running the main run loop of the CPU repeatedly because it thinks that it's exiting without errors. So if we want to make this more obvious that it's working, we can take this start and just return errors.new. I don't work. Cool. So we have a CPU that does everything but work, and we have a disassembler that does everything but disassemble. So we're making fantastic progress. And we have way too many files in my... so we're just going to add CPU, arch, arch.go. I'm going to actually commit that separately. And And this is pushed, in case you want to look closer at any of the code or diffs I just did. So we have all of this stuff, and we need a CPU loop and a disassembler, and I will try to do them quickly to make up for the technical difficulties and me fighting with my tools. So we probably need a disassembler first, because I'm going to use the disassembler to feed back into the CPU loop, so it'll just call disassemble on the current program counter. So it'll just be a loop that's like memory PC, whatever the size of an instruction is, so memory equals, and then call dismem, and get the first instruction out of that, and then switch on it. That's going to be our main CPU loop, which I will put right here as a reminder. Okay. So for our disassembler, I'm going to make, I'm basically going to turn this memory into a byte by byte reader where we can read it like a file. So give it a file-like interface instead of having to keep track of a byte position. And then we can have super lazy functions that like read a single register or opcode or something off of it. Okay, so the Go Bytes package has something called new reader, which gives us all of these handy helpers for iterating over bytes. And we're going to embed one of these in an instruction reader class. Say is new inst reader bytes.new reader. And then I'm going to define a function on here called ints that will give us a new models.ints, which was the array that we need, or the type that we need to provide by our disassembler. And I'm going to write a for loop that says basically while there's not an error. I guess I can. I'll say ints is reader.ints, and then if ints equals nil, we'll break out of the loop. Otherwise, we will add it to a list. I'm gonna models.ints and ret equals append ret comma ints. This is the cool Go array thing where we can declare an array that doesn't have any value or anything. It's nil at this point, and appending to it will create it. So now we have something here where we're going to switch on the first byte. We have r.read byte, so it's ints and switch r.read byte. This is where error handling gets awesome because you have to constant vigilance unless you start treating them like values and getting more creative about where you put them or when you check them. This is probably one of my biggest complaints with Go is having to think about errors, but I don't know, I'm sure they had reasons for making them, forcing them to be everywhere instead of exceptions popping up all the time. And read byte. So we have read byte, and we have switch. So in my opcode definitions, I created a sort of decoding table. So in defs.go, there's each of the operation types. There's the flags, which tell you what the type of the arguments on some of the opcodes are. And then there's this table that's opdata. So if I do a lookup of the opcode into opdata, then it will give me the name of the instruction and then what kind of arguments it takes. So I can just switch on this in dis.go. So I need to get an opdata. This is syntax for looking something up in a map in Go without OK is if it wasn't in the map, or if it was in the map or not. So I can say opdata instruction. Say if this syntax, so it sets these variables, and then if the OK variable was true, we're going to do this, and we're going to switch on, what's the op type? Op.arg is this flag here. So switch op.arg, and we have each of these addressing modes. So there's none, which is the opcode doesn't, or the instruction doesn't actually take any arguments. And at that point, we'll just make a new instruction type and return it. There's 1 or 2 registers, so we'll read 1 register byte or 2 register bytes out. And then there's a uint8 or uint16 immediate. And then flag, which is all of these fancy things to parse. So if it's I'm going to just copy this whole table into a switch. Of course you indented like that. Okay. So if it's none, we don't do anything. If it's 1 reg, I'm going to make an args is an arg type. So I'm going to make a type arg. I don't care what it is yet. Interface is kind of like a void pointer in Go, except if you try to use it, the type actually gets checked. So it's got some dynamic typing going on. So args is an arg interface, or array of args. And then we're going to return an instruction. Return no here. And then up here, we'll return a new instruction. Instruction type, which I haven't made yet, where the args is args. I'm actually going to call those sort of operands. Args is fine. The name is going to be data.name, and the opcode is going to be our byte there, B. So I need type, instruction type that has arg, args, etc. And we need our name, which is op. And we need our byte. We need args and name string. And I'm going to make a switching none, 1, 2 reg, 2 reg, etc. Okay, I'm going to make types for each of these. This is where I'm realizing I really should have pre-written some of these functions and said I'm going to do this and then just paste them. So u8 is going to return each of these things. So we need a u8, we need a u16, we need a reg, and flag is going to just give us an array of args. So, at this point you're probably thinking, what have you gotten yourselves into? Alright, we can switch on all of these. Oh no! Switch our flag type, flag. I think it's a byte. UID8. It's called a byte. Case any of these. Somehow. And then there's going to be an indirect type. Let's see. Make a type for each of these as well. This is a struct. So U8, let's try making it a UN8 and see if we can manage to break something. So in Go, you can put methods on normal types by declaring them as another type. I think there's pointers or something involved. We'll see. It might be doing zero cost abstractions of some kind. So type reg is going to be an int, I think, and we'll just look up the name later. Actually, there's not very many regs. So U8, U16, reg, and there's what's called an indirect, which is like an x86 assembly when you put square brackets around something. So direct is just an immediate value, and then an indirect is like move R0, R0, or move R0, some address. Okay, so with each of these we'll be returning an arg type. Which is just an interface, it doesn't really matter. Oh, I'm actually going to declare, no? Yeah, it doesn't matter. Okay, uint8, uint16 reg, and I need an indirect type as well. Which is really just a wrapper around an arg. I think that works. So now we can say oh, I need to be able to read I'm going to put an error value on here, and then if you try to read a byte and it throws an error, I'm going to write intermediate functions to deal with that, because I need to read bytes more times than I want to deal with errors. So this is going to be read 1 byte, so read 8 and read 16, which will just read from this byte reader that we have here. And it won't return an error, it will just return an uint8 or uint16 type for those other things. So R8 is the error equals I dot read byte, and then I dot error equals error return B, I guess. And then here we can't read a byte because we have a uint16, it's going to be little Indian, so we need a temporary array of 2 bytes, and then we're going to do a normal read into temp. I don't know that there's a number that we can just throw away. Never mind, we should check that. No, there's a contract on the interface, I forgot. Go throws an error if you ever read and it comes up short. Or at least any well-behaved Go interface will, or Go reader will. So we have temp, we're going to read, and then we have encoding/binary gives us a little Indian unpacker. So we can say binary.littleEndian unit 16 on our temp is a value. And instead of doing this in direction, I'm going to say set error directly. I'm going to just return this. We need to index it because usually you pass around slices, which are pointers, and this is an array type, which is the raw data. It just allows you to stack allocate an array. So we have a read 8 and read 16. So here we're just going to return a U8 type of pointer, I don't know. U8 type of I.R8. Same thing with 16. We're going to return a reg type. I.R8, which I actually have to look up in their opcode encodings. If they say, I think when I was looking at this earlier, I ended up reading the source, which is awesome. So let's take one that has a one register, so dec, and so dec RD, yeah, so it's just a byte value. So it's I.R8, and then here we can just return for each of these flag types. Actually, I'm going to skip flags for now. So one reg is going to be I.R8. So we'll do this. So 2 regs is 2 I.R8. So we're making an array here. This will allocate an array and set it to regs, so we don't have to deal with any weird indirections. Here we want an I.U8, an I.U16, and then flag is just an I.flag, which is already an array. And we need, oh, we don't actually give it the flag byte. Flag is I.R8, I believe. So we have the beginnings of something that can parse this format. This is most of a disassembler except for these flag parsings, which is just going to be calling these other functions I have up here, and the actual dis interface, which you can see on there's actually a somewhere in the models is a dis interface. I think I can actually go to type dis, which then models arch. Yeah, so these are the interfaces for the CPU builder and the ASM and des. So we need the instruction, which is here. So we actually need these 3. So we need to return the address of the instruction we just decoded, the underlying bytes for pretty printing in UIs, and then the name of the opcode and the strings of the arguments. So we'll need these helper functions eventually. So the intsreader. So on ints itself, I'm gonna move this up, and then need these functions. regardless of how far I end up getting at the 3 o'clock mark, I'm going to show some demos just to make sure the schedule is somewhat reasonable, and then I'll keep building a CPU for anyone who really, really wants to see that part too. There are some kind of cool demos in usercorn. I recommend looking at the top couple of commit messages on the Lua branch to see some of the stuff I've been working on. Just as an aside for people who might want to see the cool demos over the implementing of a CPU from scratch. So over on the Lua branch, there's a lot of stuff that's kind of cool, and you should check that out if you're waiting for me to get to something more interesting. If this is very exciting for you, then by all means keep looking at me. So we have address. I'm going to need to add adder onto this. So to implement this interface, I kind of jumped around a little bit. I'm going to stub these out for a sec. Construction, we have these things that aren't going to work yet. I.adder, I.bytes, I actually need to define on here. String, I.name, move that up one. And then obster is going to be for in range. I guess I'm actually implementing this now. In range, I.args. I'm going to do array of strings. In args. We just have to implement a string interface on each of those, each of the arg types down here, and we'll be able to print them. So then we can return strings.join args by a comma space. Okay, so what's missing here? Flags mostly, and then the helper functions on the registers, and we should have a disassembler in hopefully not too much longer than I had anticipated. So flag register, flag reg, we have something similar to down here. So I can probably do something the same way here. So var args, arg, and down here return arg. So this is register and direct, which means we need an R8 and then a U8. Direct 16. R8 and U16. This is just one reg. Direct 16 is just a 16-byte or 16-bit immediate. Direct 8 is 8-bit immediate. Reg indirect, we're just going to wrap the indirect type around an existing reg and then deal with that later in the CPU emulator. And then the printer for indirect will just print square brackets around whatever actual type it's wrapping. So this is an R8. Inside of R8. Reg indirect, direct 08. These are awesome enum names. It's an indirect R8, and then a I.direct 8 would be a U8. And then direct 16 is a U16. And then 2 reg indirects. And then 1 reg and 1 reg indirect. So that's like a move R0, R0. It's this one. Let's try building this. Oh god. Okay. A.string, arg.string doesn't exist, so I need to make the arg interface be something that at least has a .string on it. when we actually use all of these arguments in the CPU, there will be a go type switch, which allows us to dispatch based on what type the operand is. Okay, 34. We should make this one screen, and pen needs to be a slice. We need args here, not a. Reader.read at 61. I.error, oh, we throw away this returns a number of how many bytes was read, and we throw that away. I thought so. Valid pointer type U8 for composite literal. Yeah, okay, so you can't make a type of just a raw local type because these aren't pointers, so you can't like dispatch on them or anything later. So we're gonna wrap a value in them. To fix that, U8 literal is type arg. None of these implement string now too, so I'm gonna make a stupid string for each of them. Can just nope. And I need the string return type too. Got ahead of myself. And it's 75. I.R16 returns a uint16, and u16 needs u8 somehow. Yeah, that won't work. Okay. And then I.R8. Oh, reg doesn't implement string. Oh, reg's a u8. Right, all of these calls to R8 need to be calls to reg. Then arg is not an expression. Find R and R.read byte. That's I.read byte. So that's intsReader has embedded the bytes.reader, so we can just call methods directly on it by calling I.method instead of having to call like I.reader.method. It's a convenience thing. 129 op.arg, not declared. That was the, oh, that's data.arg from our opdata lookup table. This is a map of ints. I can do that. I can make it a map of bytes. A map of ints is fine. 132. These are regs. 145. Oh. This needs to not be a pointer because in Go an interface is implicitly a pointer, and models.ints is defined as an interface here. So this isn't actually a normal type. It just declares what methods are available. And new reader ended up in the wrong file. Here we need to pass the memory in. 55. We're using the attribute-based declaration here because it saves on, it just nulls any attributes you don't define. If you say like reader whatever, you don't have to define error on the type. Oh, oh. All right, And it's going to fail in the same spot because CPU doesn't work yet, but can write a quick unit test for disassembly and make sure that's kind of working okay. And then implement the proper string methods for these. And I'm not actually filling the address or the bytes of the instruction yet. So if I fill address here, implement these strings, and fill bytes, then we will have a complete disassembler for this architecture. So it's in Go, NDH, and make this test.go. Testing, so this is just the standard Go unit testing framework. If you declare a file _test, it'll build anything and call functions with this test prefix. So we just need some test data. I have just like a hex dump of some assembly from one of the files. I think this is the hello file. And then I looked up in Chrome. So we just need to import hex. It's actually encoding.hex. And this will decode a string, return a byte array. They're not equal null. Throw an error. And then we need to make a dis. And just doing this, I think. Just call a bare method on it without actually giving it a name. And it's going to be, that was the entry point of programs. And we're going to print all the disassembly. Packages are on. Oh. It printed stuff and we can't see it. Well, no, it didn't. Okay, so the disassembler doesn't do anything yet. We called dis with some mem header that wasn't getting used yet. I'm actually going to add that in right now. And I'm going to actually check the error here too. I'm not going to return it, because this is going to be a resilient disassembler where you just won't get an instruction back if you disassemble shenanigans. Syntax. Okay, so we have ints. Oh, we don't actually return ret. And R is reader, not R. Cool, we have these things that aren't printing very well. Is there a string? I'm going to add a string method on here, which Go will automatically call when printing a type. So it'll just be i.name plus i.opster plus a space. Cool. So this actually looks like the entire program. So we're just missing the argument printers and we have a disassembler. That's just going to be type U8. I'm going to use basically sprintf for this. And reg, I'm going to call num instead of val. And it's going to be r and then a number. And an indirect is just going to be a.arg plus some square brackets. And I need to import that. I hear there's a tool that'll do this automatically for you, and it's somehow never been annoying enough. I'll put some new lines in that, but it looks like we have a disassembler. Oh, I need args and or attr and bytes still. So cool. That actually looks right. So we need attr bytes, and just to save us from trouble later, if it's one of the if we're using the PC, SP, or BP registers, I'm going to return their name instead. I don't know if these are actually used in my test disassembly. Okay. And then I need to grab the address range read by, or the addresses. I need the entire bytes that were read out in the instruction. So I'm going to say bytes.reader has a equivalent. It doesn't have a tell function that tells you where you are in it, which is kind of feels like an oversight to me. It has a length and a size, so we can subtract length from size to give us a position. So if we take the length of the reader, or we take the current position of the reader at this point, before we disassemble it, and then at this point, once we have all the arguments parsed, it should give us both, or it should give us the size and allow us to get the bytes out of it. So we have I dot tell start is I dot tell here. We're going to make a byte array of that size. And then say bytes is p. And we're going to assume this will work because we're dealing with valid ranges. So we're going to do an unchecked read at of the start address with p. And then since we're grabbing this start address now, we can also say the attr of the instruction is the intsreader.attr plus the start address. And this should finish everything up except for there's some types that I need to cast, I think. So I dot size minus I dot length is your current position, and length is an int, so let's see what I missed. Oh, size is a uint, or an int 64, because apparently you can have a negative size, or they want to make it easier to do math on the size. P is byte. Oh, these are in the wrong order. And then start is type byte. Oh, it's the same error. They want in 64s anyway, so just gonna shuffle my types around a little bit. So I.tel minus start. Let's see if I missed something there. Cool. So that should be the entire disassembler interface. And let's see if I think I already added it on Arch. So once we have a working CPU, you'll be able to see the instructions it's executing. So here, I'm going to implement this for loop. So we're going to read at the begin address. Let's just set the program counter to the begin address. I don't know how I'm going to deal with error handling at this point. So if PC is not equal to the end address, then we're going to decode an instruction. So we need to in.mem read, which isn't. There's mem. This is the mem interface. There's a couple of magic methods on here specifically for reading when you're the CPU, because it needs to check memory protections. Whereas if you're reading from the API, we don't care as much about throwing the memory protection hooks, because that doesn't mean the guest did anything interesting. It's because you messed up. So read protection here. Oh, read prot and write prot will do a protected read or a protected write. And then there's also helpers, because we gave it the byte order in the memory reader when we created it, so it knows that this is a little endian target. We will be able to read integers out too. So we can read and write integers directly into memory, which will come in handy when we're actually dispatching instructions. So we want mem, so we want read prot into P with size, or at adder PC. So yeah, I'm gonna put the error outside. So if we try to read and we get nothing, we throw an error, and then we need to call dis. I'm just going to make a stack allocated disks. It doesn't even have any, it's just there to provide a method on a pointer. It doesn't have any values inside it. Can do that, yeah. So here we can just do var dis, and we can say dis.dis. It takes the memory we have. Oh, I need to allocate some memory. Mem is make byte 5, because I looked and I know that's the longest instruction we can get. There's actually a problem. If we read past a page and hit like protected memory, this will throw an error, so don't do that. I think actually in the loader we already add 4 bytes to the end, so it doesn't actually matter. So dis.dis on mem and what's this? Oh wait, we actually get to do that, I think. Because readprot actually returns. Yeah. Oh, we have to specify the protection we're reading with. So here we actually want prot exec. So we're going to read some memory with from PC, 5 bytes, and I'm going to comment the 5 so nobody gets mad about magic numbers. Say hence error equals how do you pluralize something that ends with an S in programming language? So models.inst type here. We're forward declaring these types so we can have a loop condition on the error itself. So code error equals, and then if error is not equal to nil, we're going to break again here. I'm actually going to use the condensed go if error form here to save a line, because everything else is forward declared, so it doesn't matter. And then we should be able to code comma error and then say switch instruction if len code is less than 1, then I don't know. We can come up with the real error type for that later. It's like an invalid instruction error. And then our instruction is just code 0. So we can say switch ints. We can print the instruction. I don't think I'm importing format yet. And then just increment PC by the size of the instruction. It's dot size. I guess I can make that shorthand. Just double check. No, it's a models.int, so we don't have that. So we have length of ints.bytes. And I'm actually going to print the address of, what is this A here? Trying to make sure it had the right address and it had the letter A instead, which is not okay. Okay, so we're going to print address and then just the string interpretation of the instruction, and then add. See if this builds. Probably not. Didn't import models. Prod exec isn't there. Running into type problems. A plugin that automatically suggested type things, kind of like Xcode does for, or Clang does for stuff, would be really nice. Okay, and then I don't have oh mercy, I have used printf incorrectly. I need the adder and then the instruction. And here we're fake executing. So we have the start of a CPU loop. So what remains on the CPU is to dispatch on each instruction. And I think this is basically just going to be a big switch case that takes the arguments and calls a helper function like cpu.get. So takes an arg type, and then the same thing with set, and then something to decide whether to set flags after an instruction is executed. And after that, I think it's mostly going to be a working CPU. So let's make a big switch case. Oh, this needs to be Uint64. So if you pass in the goal of this, set arg to value, I guess. So these two functions are for if you're decoding, for example, move, so case op move. That's a handy suggestion. So case op move, oh, the flags can be different on some of them. Oh no, but they're usually two operands. Okay, so case op move, we're gonna have inst.ops, inst.args 0, inst.args 1. So that's going to be like the destination and the source of the move. And we can say cpu.set args1 or args0 with cpu.get args1. So we don't have to replicate the intermediate loading code. So this will just be something that switches on arg.type, and then if it's an indirect or something, it knows how to handle it, and then uses in.memread or regread, which is actually down there, and memwrite and regwrite to actually dispatch. So I'm going to make this big, and DH. I need the opcode defs, so that's in defs.go. So I just need a big switch statement of these, which multiple cursors will happily provide me. What? Did it again. So move is there not a move? Let's move. Alright. And these are just going to be is add. Might be helpful to have some of these. Might have to look up their instruction table to implement some of these. We also need to know whether these set flags, so which ones set the 0 flag or ZF, AF, and BF. So above and below flags, I guess, so greater than and less than. So you can do a test and then jump based on whether value A was above or below value B. So, and it's going to be set flag, reg, and reg or dir. So I guess you add a reg to another arg, and takes a register and another operand. So that's set. Oh, we need another get here. So in.get inst.args 1 in dot get. I might actually do a subtable. This is going to be a bit of duplication. I could probably have a thing for up to 3 arguments. I don't actually know if any of these are 3 arguments. Push, pop, move, AB, mul, AB. No, I think these are all 2 argument opcodes. I guess if they're maximum of 5 bytes, then the only way of getting more than 2 arguments would be if one of them was a 1 byte argument. So I'm going to cheat and have a sub switch that this is inst.op here in both cases. Collects the number of arguments from each instruction. So an add is a set A with, I should totally have a table to look these up. So it's set A to B and is read A, B. No, I think it's too few instruction or too few opcodes for me to get a lot out of this. So this is going to look pretty ugly. I'll always do this. So args 0 and 1 dot set actually I can do a shorthand version of this. So I'm just going to do a simple switch statement here. So A equals inst.arg 0, B equals 1, and C equals 2. I don't think there's ever actually a C, so it's just going to be this. I don't know, they're roughly equivalent. And then here I can say dot set A to and dot get A plus dot get B, which will make this a little bit more readable. So and is reg and equals that. Call is control flow. I'll get to that later. Comp is in dot get A compared to B, so we need a greater than, less than, or equal to. So if B, then CF equals true. I'm going to need, I don't actually know which order these are in either. And I think I need to zero the other flag's truth too, so I will look into this later. So these are going to be invalid too. And Go doesn't let you use undeclared variables, so I'm just going to print. No, I'll do these up here. So before each instruction, we'll set these to the current values. No, I'll set them to the real current values. So I also can't use these because these are defined in this scope as constants. If equals, and we're going to throw away the error, equals in.reg read AF, BF, and ZF. So AF, BF, ZF, and then at the end, we'll just set them back This isn't the most efficient way of doing it, but and I'm going to do it even better. So if they're 1, it's going to set these to a Boolean. And then at the end, I'm going to set them to whether the value is a Boolean. So I can do a reg write AFBFCF to that. Wait, no. I can't go the other way. So unless you can cast a bool to an int, I don't know, and go. Nope. So this is just because the register interface takes a uint64, but all we have are bools here. So and this basically allows any of these to set a flag. I haven't decided how I'm going to handle jumps yet for control flow, but if a jump could possibly set a flag, we will need to go through these instructions, so we have to keep that in mind. And then we also have to remember that for the PC plus equals. Okay, so I can actually put that down here now. So it doesn't want to re-indent. Oh, there's errors. Defs.go. I'm going to run make on this to prefetch whatever. Oh, I don't want to make everything. Oh, yeah, I didn't get there. And this doesn't return anything, I think. And git does. Default 36. Oh, this doesn't return anything. Whatever. It's dead code now. Set args undefined. I called it something else. No? Oh, I need to cast ints to our local type instead of models.ints, which was the interface that provides all those functions. So it's 70. I don't know what's happening. Oh, there's an extra colon. I'm going to cast this back to our ints type. It'll just panic if it's not, but we got it out of our own disassembler, so it should be. And it's a pointer to ints, not an actual value that goes somewhere. How did I... Oh. No. Fine. I can't do it like that. This is just to cast the register value back to a Boolean. So A, B, and Z, all right. Well, it's still trying to run our instructions and then panics a little. Gets to the end of the file and panics. That's something I can do. There's an end instruction. At this point, we can just return in usercorn. There's a special error in models called exit status. So if the CPU loop returns that, it'll actually get shortcutted into just quitting the program with status 0. Cool. So the program works except for running any instructions. So I also run with -trace, nothing happens yet because usercorn has a bunch of debugging stuff built in, but it requires the CPU to have all of the hooks active, and this CPU is not dispatching instruction or basic block hooks yet, but that's fairly easy to fix. I can do in.on, so we have on block, on code, and on interrupt. So on block fires at the beginning of each basic block, which is when the CPU starts, or when we jump, or when we ret. So in.onBlock is going to happen at the begin address. We don't actually know the basic block size, which is the second argument, but it turns out usercorn doesn't really care, so that's okay. And then here, after we've decoded an instruction, but before we execute it, so right around here, I'm going to dispatch an on code, which is when we have an instruction, and it's going to be the address of the instruction, which is actually just PC, and the size, which is ns.bytes. And this will just call any hooks that have been added to the usercorn instance. So you can do like hook add cpu.hook code with a function that takes the adder and size of the instruction that was executed and then runs on every single instruction that's executed. And it turns out that's really useful, if a little slow in some contexts. So on code PC, we're going to have to add the basic block hook in. So this on block needs to fire sure. On block needs to fire if we ever jump to, which happens within this loop. On code, oh, I need to exit status too. There's a stop to go with start. That allows another thread to stop the CPU from running. So I need like not in.exit request. And then, sorry if I'm jumping around a little. So stop just says in.exit request is true, and start says in.exit request equals false. We call that block. Okay. On block, on code, and there's a syscall instruction that's going to use the on inter hook, so on interrupt, and it now is 0, don't care. So we just want to signal that a syscall should happen. So on code has the wrong type. This needs to be init 32, unit 32. And it panics with a missing syscall, which makes sense because the syscall decoder doesn't do anything yet, and the instruction that moves a number into a register to call a syscall doesn't do anything yet. I don't know why this isn't tracing, or the instructions aren't tracing. Heading, oh, I changed something, that's why. This would have actually already been working to some degree. So here, I'm going to delete all these prints. We don't need to print those anymore because they're getting used. Go doesn't let you just have a variable and not use it, but they're getting written back to the registers. These flags are. Okay, so this should actually print instructions from the usercorn tracing infrastructure. So this is usercorn's UI already knowing about, it basically hooks into the disassembler with the interfaces that have been given. It knows how to start the CPU. It loaded everything into memory. It started executing, and it's actually tracing memory I/O at this point, but this is where the registers would go. We aren't actually implementing the instructions, so registers aren't changing, and control flow won't really do anything at this point, and syscalls don't do anything at this point. But otherwise, it's most of the way there. So copy pasting these, op and dec is a's, and I get a -1, div is an arithmetic one, so a divided by b inc will be a +1. I should really be looking at the documentation for these, but I'm just intuitively implementing things because they said it was based on x86 and ARM. Move is a equals b. Mul is arithmetic again. I'm just going to skip over the not case. Not is probably going to be a invert of a. This is the equivalent of the tilde in Go. I don't know why it's a caret. They also have their own assembler. Or is A or B. Push and pop are going to need. We actually need to read the stack pointer and do some stuff there. Ret is a TBD, so these are all the jumps. Syscall. I'm gonna actually put the jumps at the end so I can deal with them separately. Of course I want blank space between these. And I'm missing call, I think. It was way at the top. I promised I was going to switch to playing with the exploit stuff, but I think I'm about 5 or 10 minutes from having this done, and it would be cooler to do it with the CPU that you saw get implemented on screen than some stuff I've already built. So I'm going to push forward. If you are getting really excited about seeing exploits and can't bear to watch another second of me pasting stuff into a switch statement, go eat a sandwich for like 15 minutes and we'll probably be exploiting stuff after a quick bathroom break. Or reversing at least at that point. Okay, sub is a minus b. Test is going to be a compare. Exchange probably grabs a and b. Swaps them. I'll go read the docs after this to make sure I didn't miss anything. It's faster to just implement these intuitively. So we're going to exchange A and exchange XA. XOR is another arithmetic one. I'm going to move test out here down to this. And I'm going to move NOP to the bottom. So all the arithmetic and stuff, and move comp out as well. So the stuff at the top is going to be mostly organized. And then push and pop are going to come out too. So we have arithmetic ops, font size. We have push and pop. We have compare, test, and then all these. Where did end go? And they'll come out to the control flow ops as well. So it's kind of like control flow. Cool. Op test is, I don't know. Is that equal? This doesn't actually explain the instructions. So I guess it's good that I have been implementing them without the explanation. Does this explain? Okay, it takes 2 operands and I'm guessing tells you if they're equal, unlike compare. Does test not set greater than and less than? Okay, yeah. So comp sets AF and BF and nothing else does. and then 0 flag is test. So test is n.get a equals n.get b, so zf equals. So these I think take a, I think the jumps are all relative. So like this is a jump back a couple instructions, whatever that is in not unsigned integer form. So these are all going to be grab the operand. In fact, all of the jumps are going to be n.get a, and then some of them are conditional. So jump L and jump S are actually the same implementation as well, I believe. And these are FCF. Growls apparently looked it up, and test is whether both arguments are 0, which is kind of obnoxious. I don't actually know what the x86 test does. I assume it's in the same realm. I don't know what happened to the white space again. Every once in a while the white space just does something wrong. Okay. No, that's not FCF. J and Z is not ZF. JZ is FCF. We're going to set the jump offset. And out here, before the big decoding table, I'm going to say jump off is 64 set to -1. No, that's too good. I don't know, because you can have negative and positive jumps. Oh, it doesn't matter if it's it has to mask to 32 bits. I need some way of saying whether a jump is set or not. Oh, I could just actually take the target address. So yeah, this is just going to be a uint16 that says which address we want to jump to. Otherwise I need some way of controlling the state. And instead of a uint16, I can set it to an int32 and have it be -1 to start. So we know if we didn't jump. Because somebody might actually jump to 0. Because it's all mapped, or it can be. The stack is between 0 anyway. So XOR is actually still minus, apparently. Sub syscall is more of a control flow than anything else up here. Just basic checks. Alright, push and pop are going to need memory operations and reading the stack register, which I don't want to deal with yet. Call is another push. JA is if AF. JB is if BF. L and S are unconditional. Ret is another stack, so call and ret are going to go next to each other. And push and pop are going to go down there too. So the jump offsets are from the end of the instruction bytes. So I'm going to pre-grab that up here as well with all the 0 flags. So jump base, I'm just going to call it ints end is ints.adder plus lane ints.bytes. Just going to see if anything's not building. Literally the last thing I did. I needed a uint64. I guess lane only returns int, which is confusing to me. You can't have a full single address. Oh, jump off is not set. And that'll be the ints end. And I guess I will just truncate that to 32 or 16-bit integer down here. So if jump ABS not equal to, or jump ABS greater than or equal to 0, then we're going to jump, and then jump ABS equals 0. Force it to the 16-bit space, and then print the jump target. Actually, I don't even need to do that. That's code duplication 2. I can do jump off, and these will all be positive uint 16s. So this doesn't need to be a, yeah, no, int 32 is fine there. I just need to cast these to an int 32. It's not possible to set them outside the int 16 range, or uint 16 range. And then if jump off is greater than 0, we take the ints dot adder. Did I already calculate ints end up here? I'll just steal that. And we just say ints in plus uint 64 jump off, because the address space in usercorn is uint 64. So there's 64-bit address space. Everything's kind of crammed into. And we'll set the jump offset back to 0. So actually, now we're up here, it's fine. And then else, we increment the PC. And I guess here we should just set the PC to ints in plus uint 64 jump off, and then just say that we did jump. Just make sure this is working. Somehow I'm still using jump off a bunch. Oh. Builds. Registers aren't tracing. I don't actually know if instructions are executing correctly or not at this point. I guess not, because, oh, I haven't implemented get and set, that's all. So syscalls are unimplemented, but that should be a pretty simple table. Jump off equals, call is jump off equals, and should push ret adder. Ret is pop PC adder. And continue, I guess. I guess I could turn it into a jump off by doing PC minus ret or something. And then push and pop are, oh, I needed to actually need to do this masked to, I removed that at some point when I was refactoring that. Okay. Otherwise you'd be able to jump past the end. This needs to set jump off too. So I need push and pop, and I need this. Where's getting set? It's just some helper. Put this up here somewhere. So I need getting set. So I'll do a case. Each of the types. So it should be this and getting set, and we should have a semi-working CPU. with like full tracing and instrumentation and everything. So I need to look up the different types again because it's been a while since I wrote that. So ints is args. So it's either a direct or indirect, one of these three. It's fairly simple argument types. So if we're getting or setting indirect, we actually need to read memory. Otherwise, we just take the value directly. So what we actually just need to do here is take the value without direct, and then does set need to actually get the, like if it's move R0, 1, set needs to do a get, so indirect case needs to do in.get arg equals val, I think is all. So I could recurse on that. And this could actually cause infinite or semi-infinite recursion, but nobody's actually going to, because we wrote the disassembler, it's not a problem to just blindly recurse. So in.set, in.get adder, or in.get v, val, and then the other ones are case, reg, and you can't actually set, oh, you can set an indirect adder. Oh, that's a problem. So if it's indirect, we'll recurse on a reg. No. Just set get. Yeah, this is memory. This is a special case. Never mind. I didn't think this through enough before starting to talk about it. So if we hit a register and we're not indirect, all we have to do is say in.reg write. I think the register numbers are already lined up. I don't remember. So I'm going to close some of this. dh.r0. I guess it's 0 and up. So yeah, 0 through 7 is the first ones. And 8, 9, 10, and then the flags aren't real registers. Okay. So I'm going to assume the register numbers match the enums at this point, and if it breaks, I'll fix it. So in.reg write, we're also still not going to check for errors here. Do a reg write with our v.num and the val that was passed in. You can't set non-register indirects, so you can't set, yeah. If it's not indirect, only regs are the other case. And we could add a default case, but we're going to print the type of the thing you tried to set. If you try to set something that doesn't make any sense. Okay. So if you get an indirect, we're going to switch on the subtype. So v.arg, we can actually just override a here because we don't need the a that was at the top scope. So switch, and then we say, or, we don't actually even need the indirect other than to tell us that it was an indirect. So if we have case u8, case u16, these should be actually the same again. And then case reg, and then we say, I'm just gonna set an address out here. And say adder equals n.get. N.get value. Actually, can we just do that? Okay, I think memory reads are actually only 1 byte, so it's only used on move. Okay, so there's no durate or dir16, it's just durates. So here we could just cast it to reg. It's only reg and direct here. So, R is, this will just panic if it's not actually a reg. It's v.arg.reg and.get R. Actually, just keep piling on the parentheses here. It's adder is that, and then in.mem. Write uint, that's what we want, and it's prot write, and I think it'll actually give me the, yeah, so we want adder, size is 1, prot is cpu.prot write, and it's already val. Cool, so we get a reg, and then case anything else, so if you, oh, you can't actually set numbers, that doesn't make any sense. Yeah, you can only move to a reg or a reg indirect. You can't move to a normal memory address, so that's even easier. So then in cpu.get, we don't need that anymore. We just do a similar switch case. If it's an indirect, it's only used on registers still. So we just need a read uint here with prot read instead. These protections allow the underlying MMU to enforce the protections on the page. So if you read from a page that doesn't have the read protection and you specify that you want to read with prot read, it will fail. These could have been implicit, except you can read with both read and exec. Execute and read permissions are different. So read. Just going to call this in unit 64, and in equals, I assume there's an error, but I don't care too much. Actually, I'm going to set, I think I have, I'm going to set in.error. And it'll just fail at the end of the instruction. So in and in.error equals that. Actually, it should fail earlier. It's not a super good solution to this, because it's not going to finish executing the thing that failed. Or it shouldn't finish executing the thing that failed. I think I'm going to punt on this because it would take too long to solve properly for now. So, and then we don't need to care about the value of reg reads, or the error value of reg reads. And then if it's a case, uint, or u8, or u16, then we say in equals unit 64 v.val. And I think that's all the types. And I need to return n instead of 0 here. switch this back to one pane. Too many errors. You got that right. Cannot use v.num type u8 as type int. I have to do casts on all of these. Oh, in is already the name of our CPU. No. Okay. Nope, not these ones. I don't know how to unselect. Call it val instead. Prot read doesn't take a reg read, doesn't take an argument either. CPU is executing, or even jumping. I'm going to delete that printf now. I'm going to turn this one to a panic. Actually, this should just be an unknown op error. Syscall table here, systems. How are you doing that? Oh, we have a hello world. We have a bunch of blank space here. So our program is executing. I don't know why this is blank. I assume because somebody did a jump to a no? There might be an instruction decoding issue here. But the program worked, which is confusing for all the blank space. Oh, we are jumping and we aren't issuing a new basic block hook. So the tracer doesn't know where we are. So I just need to copy the on block into the jump handler up here. And it should trace the full hello world. Boom. It's most of a CPU. I'm going to push what I have. I guess we don't return errors here anymore either. R.error. All right, I'm going to implement the stack operations. So we need call and ret. And I'm going to go to the bathroom and work on an actual reversing challenge. Not at the same time. So we just need to push and pop, which means we need to grab the stack pointer. I'm just gonna pile it onto the stuff I'm reading up here. There's a lot of function call overhead for fast CPU, but this doesn't need to be a fast CPU at all. So nobody's written more than a couple kilobyte program in it. So we need a reg read SP. Actually, we can even just make a push and a pop. It's always, wait, does pop take arguments? Oh, great. So we can push a 8 or 16-bit. And then, all right, I'll read it here and just manually do math on it. So call pushes ret editor. So we do r dot error equals, this isn't r, this is n. N dot error equals n dot mem write uint with, I wanted the completion. So the adder equals sp, the size equals 2, prot equals prot write, and the val equals current PC plus, I'm just gonna make a, yeah, I'm gonna make a next PC up here. Can reuse it instead of duplicating that code. And here, just use next PC, and then sp minus equals 2, stack goes down. Here we do an n dot read uint. Actually go on the other. N dot read uint sp. Forget if pop or which order the pop goes in. Okay. Read uint sp to cpu.prot read. So this is, I'm just going to set jump off equals, so off uint 64. Nope, it's not. Oh, yeah, it is. So then jump off equals int 32. PC minus off. And you add that back, it should give you the new PC address. It's just so I can reuse this code down here. And then push and pop are going to be, I don't remember which order this goes in. I'm a little hazy right now. Just going to be the same, but with more than one type. So we need the size of, no, pop is always reg. So pop is just n.read uint sp to CPU prot read. Then, no, I need to set n.error every time. Then I n.set a with val. And push can be register or an immediate. So I'm going to switch a.type case reg, case u8, case u16. And I'm going to subdoing code duplication. Oh, I need size too. All right, so in.get a is the val, size equals 2, size is just going to be 2 by default, so U8 will set size to 1 by hand. Just reuse the size here. Nope. And val equals uint 64 v.val. Actually, get will already do that. So I just don't know the size. So if okay is so if it's a U8, I have to set the size to 1. That's all I have to do here. And then push is SP minus 2. And I'll fix these stack pointer errors in a second. Here I have to fix the stack pointer, so in.regwrite with our new SP, and then here we've got ret adds the stack, pop reads and adds. And this is next PC, it needs to be val. So SP minus first, second, I'll move that down. I'm going to put these in the same order so I don't get as... Okay. See how I did. And that's a problem. I need the OK from this too. In SP size. Graz is telling me that it doesn't matter if I actually read the correct size. So all right, apparently you always push and pop by 2, so I don't even need to do this. It's even simpler. I'm sure I'm missing something. Where was my dot slash? Here's a program. Let's try running one of the more complex samples. It's NDH samples slash crack me one. Ret is doing a panicky OF. Oh, ret must be wrong. So PC minus off. Oh no, it's adder. I do push. Nope, I've been told that it is how it was implemented. I'm going to undo it back out. So op push 8 does do that. Oh, that's ret. I need it. Oh, come on. Super fancy undo buffer. Does it write to each time? Oh, okay, no, because this one does a cast unit 16 and this one doesn't. Okay. Ret and call are broken, so I probably did something wrong with the stack here. SP minus equals size. Building. I'm going to push this. So here we have added push and pop and probably gotten them wrong. But I'll push anyway, because a real example is failing. All right. Oh, we're actually messing up the stack here. So we've got, looks like a stir lane where you're incrementing two numbers. Actually, this is, they include a standard library at the beginning of the assembler, and stir lane is always at this address too. So that's handy. 8003 is stir lane. They do a bunch of increment, jump not zero, and then move R1, the address of R0, and they increment the length and the pointer to the string repeatedly. So this is probably trying to print something. So we've got stack being set. Oh, wait a sec. This piece starts at 8,000. I do remember from the spec, they also set a base pointer that I need to deal with in here. So this is going to be 8,000 anyway. Whatever, I'll read it out. Something's off with my stack pushes and pops though, because I'm hitting a, I think I'm running out of bounds on my stack. Yeah, my stack pointer ends up at 8,002, which isn't right. I'm going to copy this into Sublime and highlight all the stack pointer equals. So we have a call, it decrements by 2. Call by 2. This is awesome debugging time. We have a pop, ret. Pushes, pops, and then rets. I don't know how this is off. Maybe I jumped on bad offset. The stack would get blown off if I jumped to the wrong spot too. Some basic self-code review. And hopefully get to super exciting stuff soon. Okay. Just double check all of my ops too. Read all the flags. Oh, do I actually? The right order for comp? Shouldn't matter for stack position. Alright. A plus B, A and B, A minus 1, A divided by B, A plus 1, A equals B, A times equals B. Okay. Or how do people feel about taking a like 20-minute break and I will come back and start a new stream versus taking what I've done here and showing off cool stuff tomorrow or next week? Oh, the flags need to be set on more instructions. All right, let's say I will poke at this on stream, but I won't do anything exciting until at least 4:15 Pacific, so in 20 minutes. So the entire reason we're building a CPU emulator on usercorn is to get access to some of the cool tools it has. And this is one of them. It's a Lua REPL. It allows doing a bunch of stuff intrusively to the program, like patching. And that's an op now. And something that I just landed this morning that seems to work pretty well is a feature that rewinds the execution of the program while it's being debugged. So you can like rewind 5, which puts you to the move EBP ESP. And now if we step forward a couple more times, we'll get back to where we were. And this is actually taking, basically usercorn traces the entire state of the CPU as it's executing and can undo parts of it or all of it up to any point. If I run this on If I run until I hit a syscall, and then I run it, here's like a hello world print, and then I can rewind one, and then step, and I get another hello world print, for example. I don't know. I will take a short break and then fix whatever problem is